Welcome everyone to the second lesson of this course, General Relativity for Betas. So, in this lesson, we'll learn about two important objects for theoretical physics, which are written in index notation. So, first of all, as a little disclaimer, every index that I'm going to write is going to run from 1 to 3. So, having said that, let's begin with the Kronecker Delta. And this object is written as a delta with two indices. Now, this is something new because in the previous lesson, we only saw objects with one index and those were vectors. So you might think, what are these kind of objects or what is the analogy? So we'll see in later lessons that we can represent these objects as matrices, but they are not really matrices. Okay? So this is an object which has components depending on the values that we give to the indices. It can oscillate between two values. The Kronecker delta equals 1 if the two indices are equal, and it equals 0 if the two indices aren't equal. So let's calculate some components to see how this works. So delta of 1, 2 is going to be 0 because the indices are different. Delta 3, 3 is going to be 1 because both indices are equal. Delta 3, 1 is going to be 0 because the indices are different, and you get the idea. So now we may ask, wait a second, how many components does the Kronecker delta have? So let's remember that the indices can run from 1 to 3. So we have two slots, the first being the I index and the second the J index. And for the first index, we can pick one out of three numbers. We can pick 1, 2, or 3. And after this number that we have picked for the first component, now we can pick any other of the three numbers. So it's also 3. So this results in 9 components of the Kronecker delta, and they are not too many, so we can write them all explicitly. We have delta 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. So you might now see the analogy with the matrix representation, but we'll see this in later videos. And that's it. I mean, that's the Kronecker delta. It's a very simple object. You can calculate all of its components by this basic rule. And you can even extend the definition to being the indices run from 1 to n, and this still applies, okay? But we said that we are going to stick only with 3 numbers for the components. So, to learn about the next object, which is, spoiler alert, the Levi-Civita symbol. Well, it's not spoiler because it's in the title of the video, so anyways. We need to learn about something which is permutations. So, let's say that I have 3 slots, okay, I, j, k, and I want to put some numbers in there, of course from 1 to 3, but I don't want the numbers to repeat. So, for example, if I put in the first one the number 2, then I can write the number 1, and then I cannot repeat the 1 or the 2, so we are only left with the number 3. Okay, so let's see how many possibilities we have with these rules. For the first index, we can pick 1 out of 3 numbers, so we have 3 possibilities. Now for a second index, we have chosen 1 number out of the 3, so now we can only pick 1 out of 2 numbers. And for the third index, we are only left with 1 possibility because two of the three numbers have been chosen. So this gives us 6 possible numbers. We have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So we're going to define what is an odd and an even permutation, comparing this other order of numbers to this one. So we are going to call 1, 2, 3 like the standard order. And now we are going to say, how many permutations do we have to do to this number to arrive at this one? So we call a permutation a swap of numbers. So let's say, for example, that we are going to swap the 3 by the 2. So we now have 1, 2, 3, and we have arrived at the standard order. So we have made one permutation. And the number 1 is odd. So we define that this sequence of numbers is an odd permutation. So we can say that the sequence 1, 3, 2 is odd. Well, an odd permutation, okay, to be explicitly. We can do the same for the other sequences. Let's, for example, to this number, we can exchange the 1 by the 2, and we have 1, 2, 3, and it's the same thing. We have one permutation, thus 2, 1, 3 is an odd permutation. Now let's see this one. Here we can exchange the 1 by the 2, and we will have 1, 3, 2. Now we can exchange the 3 by the 2, and we have 1, 2, 3. So this time we have made 2 permutations, and 2 is an even number. So we are going to say that the sequence 2, 3, 1 is an even permutation, and so on with the other sequences. Okay, if we do this fast, we can see that here we can interchange the 1 by the 3, and then we can interchange the 3 by the 2, and we arrive at the standard. So this is going to be also an even permutation. And now here in the 3, 2, 1, we can exchange the 3 by the 1, and it's just the standard order. So this is going to be an odd permutation. We can also define this, the standard order, as an even permutation, because we have done like 0 swaps of numbers to arrive at 1, 2, 3, and 0 is even. So we are going also to define this as even, okay, an even permutation. So there's another trick, okay, if you don't want to swap numbers, but I highly recommend you to learn how to swap numbers to see if a sequence is even or not, because the trick that I'm about to show you only works in 3 dimensions. So the trick is the following one. Let's erase this, because otherwise we are going to know all the examples that I'm going to write. And let's say that we want to know what is the permutation 2, 3, 1. So what we are going to do is to write this number 2 times, or even 3 if it's not enough. And now we have 2, 3, 1, 2, 3, 1. And now we are going to search for a 1. This one, which is in the middle. Now we have to make the question. To make the standard order, do we have to read to the right or to the left? So in this case, if we go to the right, we have 1, 2, 3. So we can conclude that this is an even permutation. Now, let's say that I have the 3, 2, 1, okay? And let's do the same trick, 3, 2, 1, 3, 2, 1, and we pick a 1 in the middle. So now it's the same question. Do I have to read to the right or to the left to read the standard order? So in this case, it's to the left. 1, 2, 3. So when we read to the left, now this is an odd permutation. Okay, so when we read to the right, the sequence of numbers is an even permutation, and when we read to the left, the sequence of numbers is an odd permutation. Okay, so this is a little trick that works, and just for you to know. But I highly recommend you to get used to swapping numbers. So now that we have explained a little what are permutations, we can explain the Levi-Civita symbol. and this is written as an epsilon, not 1 nor 2, but 3 indices. Well, you might have guessed this because of the explanation of permutations, where we had 3 slots. And now if you calculate the components, we have 3 slots, I, j, k, and we can repeat numbers now, okay? Now, and then I will explain why I only wanted to see permutations with non-repeat numbers, okay? So we have running indices from 1 to 3. The first one we can pick 1 out of 3, the second one also, and the third one also. So these are 27 possibilities. So this the Levi-Civita symbol has a lot of components, not as the Kronecker Delta, which only had 9. Now the rules for calculating the components are this one. The Levi-Civita symbol is 0 if any of the indices repeat. It's going to be 1 if ijk is an even permutation. And it's going to be -1 if ijk is an odd permutation, okay? So even positive, odd negative, and if any of the indices repeat, it's going to be 0. So some examples: if we have epsilon 1, 2, 2, it's going to be 0 because we have the 2's repeated. Epsilon 3, 1, 3 is going to be also 0, and so on with any repeat indices. Now we are going to write a sequence of indices which doesn't have repeated indices, and we are going to apply our knowledge about permutations. So let's say we have epsilon 2, 1, 3. So we can see that we swap one time 1 by the 2, so it's an odd permutation, or we can do the trick 2, 1, 3, 2, 1, 3. We pick this one, for example, and we go to the left to read 1, 2, 3. So we are going to the left, so this is odd, and if it's an odd permutation, then it's -1. Some more examples are, for example, epsilon 1, 3, 2. We swap the 2 by the 3, so one time it's odd. Now we have 1, 2, 3. So now we can swap the 1 by the 3 and the 3 by the 2 times, so it's going to be even. Or we can write 3, 1, 2, 3, 1, 3, 1, 2, 3, 1, 2, and when we pick 1, 1, we are going to read to the right, so this is going to be even also. So it's 1. We also have 2, 3, 1. We can swap the 1 by the 2 and the 3 by the 2 times, so this is even, and you get the idea. So we saw previously that we only have 3 times 2 times 1 components of numbers, of sequence of numbers that don't repeat any index, and in total we have 27 components. Okay, this is total, and this is non-repeat indices. So we can see that we have 21 components that are 0. Okay, because from the 27 total components, only 6 have non-repeated indices. The other 21 have any 2 indices repeated at least. So most of the components of the Levi-Civita symbol are 0. We only have to care about 6. So you might now think, okay, how can I use this? Because I mean, okay, and this is very interesting, and all the rules, the conditions, and there are interesting objects, but how can I use them in physics? So we'll see this in the next lesson, where we are going to relate the Kronecker delta with the scalar product and the Levi-Civita symbol with the cross product of vectors, of course. So see you in the next video, and if you have any doubt or any suggestion, please write in the comment section, and I gladly reply to you. Bye.